Hello, friend. Welcome to another quiet journey through the cosmos. Some nights when the air is still and the world has folded itself into silence, you might find yourself staring up, not searching for anything in particular, just looking. And in that looking, something ancient stirs, a question older than cities, older than written language, a question whispered by every human who ever lived beneath an open sky. How many stars are there? It sounds simple, doesn't it? Like counting stones on a beach or birds in a tree. But here's the thing about stars. The moment you think you've counted them all, the universe leans in close and whispers you've barely begun. Before we drift into this story together, I want to say thank you for being here, for choosing this quiet corner of the night. If these soft journeys through science bring you peace, you might like to stay a while longer. You can gently tap the like button if this resonates with you. Subscribe if you'd like more stories told softly, and ring the little bell, not for noise, but so the next quiet night can find you again. There's no rush. The stars have waited billions of years. They can wait a moment more. Now, let's drift. Tonight we're going to follow a question across thousands of years. A question that has humbled kings, obsessed philosophers, and driven astronomers to the edge of madness. How many stars fill our Milky Way galaxy? The answer has changed so many times in so many ways that the story itself becomes a mirror. It shows us not just what's out there, but how we see, how we count, how we try to hold infinity in our hands. Let's begin where all star counting begins, with eyes wide open under a sky unmarked by city lights. Imagine you're standing in the desert 4,000 years ago. No buildings, no streetlights, no glow on the horizon. Just you, the sand, and the dome of night, pressing down like a cathedral made of darkness. You look up, and you see more stars than you ever thought possible. They dust the blackness like sugar spilled across velvet. The ancient Babylonians stood beneath this same sky. So did the Egyptians, the Greeks, the Chinese astronomers, who carved their observations into bone and bronze. And they counted. Oh, how they counted. Not because they needed to, but because the human mind does this thing where it tries to contain the infinite. It tries to name what cannot be named, to number what cannot be numbered. The Babylonians divided the sky into constellations, mapping stories onto random scatterings of light. The Egyptians aligned their pyramids with Orion's belt, as if architecture could hold a conversation with the heavens. And the Greeks, ever curious, ever insistent on order, tried to catalog it all. Around 150 AD, a man named Claudius Ptolemy sat in Alexandria, Egypt, surrounded by scrolls and star charts. He compiled something remarkable for his time, a catalog of stars. He listed 1,022 of them. That was the number. 1,022 points of light, each one given a place, a brightness, a meaning. For over 1,000 years that number stood. People believed Ptolemy had counted them all. The visible stars, the knowable stars, the stars that mattered. But here's what Ptolemy didn't know. He was wrong. Not just a little wrong. Magnificently, beautifully, cosmically wrong. Ptolemy could only see what his eyes allowed. And human eyes, for all their wonder, are limited instruments. Scientists now estimate that from any single location on Earth, under perfect conditions, with no moon and no light pollution, you can see between 2,000 and 3,000 stars with the naked eye. If you could somehow stand at both the North and South poles and combine every star visible from each hemisphere, you'd reach maybe 6,000. Some estimates push it to 9,000 under the most pristine skies Earth has ever offered. But Ptolemy didn't have pristine skies. He had oil lamps. He had cities. He had the same atmospheric haze, the same dust, the same limitations that every ancient astronomer faced. So, his count of 1,022 wasn't complete. It was a guess, a beautiful, ambitious guess, but still a guess. And yet, for over a millennium, people accepted it. Why? Because it felt complete, because Ptolemy was trusted, because the idea that we had counted all the stars was comforting. It meant the universe had edges. It meant We could know it, hold it, finish it. Here's where the first mistake lives. Not in the counting itself, but in the assumption that what we see is all there is. Ptolemy saw 1,000 stars and thought this is the sky. But the sky was hiding most of itself. It still is. Let's talk about brightness for a moment. When you look up at a star, what you're seeing isn't the star's true power. You're seeing its apparent brightness, the light that survives the journey to your eye. Some stars look dim, not because they're weak, but because they're far away. Others blaze brilliantly not because they're titans, but because they're close. Ancient astronomers didn't know this. They assumed bright stars were important, and faint stars were lesser. They built mythologies around the bright ones, gave them names: Sirius, Arcturus, Vega. The faint ones were backdrop, decoration, barely worth counting. Hipparchus, a Greek astronomer who lived about 300 years before Ptolemy, created one of the first true star catalogs. He measured the positions of around 850 stars and ranked them by brightness. He invented the magnitude scale, a system we still use today. The brightest stars were first magnitude. The faintest stars visible to the eye were sixth magnitude. It was elegant. It was systematic. It was also based entirely on what he could see, which was a fraction of what was actually there. Here's a thought that might pull you deeper into this quiet. Every star you've ever seen with your naked eye, every single one belongs to our galaxy, the Milky Way. Even Andromeda, the nearest large galaxy to ours, appears as a faint smudge, not individual stars. So when ancient people looked up and saw thousands of lights, they weren't seeing the universe. They were seeing their neighborhood, a single street in a city of billions. And they didn't even see the whole street. They saw the brightest houses, the ones with the lights on. The rest stayed hidden in the dark. Now, let's talk about what modern science knows quietly without fanfare. The Milky Way contains somewhere between 100 billion and 400 billion stars. That range, that enormous gap between 100 billion and 400 billion, tells you everything you need to know about how hard this question is to answer. We can land robots on Mars. We can measure gravitational waves from colliding black holes. But we still can't count the stars in our own galaxy with precision. Why? Because most stars are dim. 70 to 80% of all stars in the Milky Way are red dwarfs, small, cool, faint stars that barely glow. You can't see them without a telescope. Even with a telescope, they're hard to spot. They don't announce themselves. They don't burn bright. They just exist quietly, doing their work of fusing hydrogen into helium, living for trillions of years in near invisibility. Ptolemy's 1,022 stars represented about 0.0001% of the Milky Way's total stellar population. Imagine trying to understand the ocean by counting the waves you see from the shore. That's what ancient astronomers were doing, and they didn't know it. Here's another layer: light pollution. In Ptolemy's time, the night sky was darker than most of us will ever experience. But even then, cities existed. Alexandria was a bustling port. Fires burned, lamps glowed. The sky wasn't pristine. Today, more than 80% of the world's population lives under light-polluted skies. In most major cities, you can see maybe a few dozen stars on a clear night. The Milky Way itself, that river of light our ancestors knew so well, has vanished for billions of people. We've traded the stars for streetlights. Studies show that someone living in a modern city might see only about 200 stars on a clear night. 200 out of hundreds of billions. We're not just undercounting. We're living in a kind of cosmic amnesia, forgetting that the sky was ever full. But let's return to those ancient counters. Let's honor what they did. Because even though they were wrong about the number, they were right about the impulse. They looked up and felt something: wonder, curiosity, a need to know. And they did what humans do best: they tried. They built tools from thought. They created systems. They passed their counts down through generations, refining, questioning, revising. The mistake wasn't in counting. The mistake was in stopping, in thinking they had reached the end, in believing the sky had given up all its secrets. Every generation of astronomers has made this mistake. They count what they can see, then assume they've seen it all. Then someone invents a better tool, a sharper eye, a longer reach, and the numbers explode. The universe expands not because it's growing, but because we're finally seeing what was always there. So, here's the truth we're going to carry through this journey tonight. The question, how many stars are there, has never had a final answer. It's had 1,000 answers, each one a snapshot of what we knew at the time, each one incomplete, each one beautiful in its incompleteness. Ptolemy counted 1,000. We now say hundreds of billions. But even that's not the end, because as we'll see, the count keeps changing. Stars are born, stars die. And the tools we use to see them keep getting better, reaching farther, seeing deeper into the fabric of space and time. You don't need to memorize the numbers. You don't need to hold them. Just let them drift past like clouds. What matters is the motion, the reaching, the way each answer gives birth to a new question. The ancient astronomers stood beneath the stars and counted what they could. They were humbled by what they saw, but they had no idea how much the universe was hiding, how much darkness held light they couldn't touch, how many stars waited silent and patient for someone to invent the glass that would reveal them. And that's where we'll go next, into the moment when everything changed, when a simple piece of curved glass turned the sky inside out and showed us for the first time that we had been living inside a secret too vast to comprehend. The telescope was coming, and with it, the first true shock of scale. The year is 150 AD. Ptolemy finishes his star catalog and sets down his stylus. He believes he has captured the heavens. 1,022 stars, each one measured, each one placed. The work is done. The sky is known. Except it isn't. Not even close. Let's sit with that mistake for a while. Not to mock it, but to understand it. Because it's a mistake we still make today in different forms, with different tools. We see what we can see, and then we stop looking. We call it complete. We call it truth. And the universe waits patient as stone for us to realize we've barely scratched the surface. Ptolemy wasn't alone in his error. Every ancient astronomer carried the same blind spot. They assumed the stars were fixed, permanent, unchanging. The term fixed stars became doctrine. The stars were painted on a celestial sphere rotating around Earth, never moving relative to each other. This wasn't just science. It was philosophy. It was theology. If the stars were fixed, then the heavens were perfect, eternal, divine. But the stars aren't fixed. They move. They're born. They die. They drift through space at speeds that would shatter our sense of stillness if we could see them in real time. Barnard's star, a red dwarf just 6 light-years away, moves across our sky faster than any other star. In a human lifetime, it shifts position noticeably. Ancient astronomers never noticed. They weren't looking for motion. They were looking for constancy. Here's the mistake beneath the mistake. They confused what they saw with what exists. If a star was too faint to see, it didn't make the list. If it moved too slowly to detect, it was called fixed. The catalog wasn't a map of reality. It was a map of perception. And perception, no matter how careful, has limits. Let's go back further. To Hipparchus, the man who created the first systematic star catalog around 129 BC. He measured the positions of roughly 850 stars. He noticed something strange. When he compared his measurements to those made by earlier Babylonian astronomers, some stars had shifted. Not much, just a little, but enough to matter. He called this precession the slow wobble of Earth's axis that makes the stars appear to drift over centuries. It takes about 26,000 years for Earth to complete one full wobble. Hipparchus didn't know why it happened, but he saw it happening. And that tiny observation cracked open a truth. The heavens weren't as fixed as everyone thought, but even Hipparchus made assumptions. He ranked stars by brightness, creating 6 categories. First magnitude for the brightest, sixth magnitude for the faintest visible to the naked eye. It was a scale based entirely on how things looked, not how things were. He didn't know that a dim star might be a supergiant billions of times more luminous than our sun, just sitting very far away. He didn't know that a bright star might be a relatively small nearby object punching above its weight simply because it was close. This is the problem with apparent brightness. It lies, not intentionally, but structurally. When you look at Sirius, the brightest star in our night sky, you're seeing a star that's about twice the mass of our sun, sitting 8.6 light years away. It looks brilliant, but compare it to Betelgeuse, a red supergiant in the constellation Orion. Betelgeuse is about 700 times the diameter of our sun and over 100,000 times more luminous. But it sits roughly 550 light years away, so it appears dimmer than Sirius. If you swapped their positions, Sirius would vanish into faintness, and Betelgeuse would dominate the sky like a second sun. Ancient astronomers had no way of knowing this. They saw brightness and assumed importance. They built myths around the bright stars, named them, worshipped them. The faint ones were extras, background noise, nameless sparks barely worth recording. Here's another layer to this mistake: cultural bias. Different civilizations counted stars differently, not because the stars changed, but because the stories changed. The Chinese identified roughly 1,400 stars by the time of the Han Dynasty. The Arabs, building on Greek and Babylonian knowledge, cataloged over 1,000. Each culture saw the same sky, but counted it differently depending on what they valued, what they needed to navigate what their myths required. The sky wasn't objective, it was interpreted. And then there's the problem of the naked eye itself. Human vision peaks at a certain wavelength, around 550 nanometers, which corresponds to green-yellow light. Stars that emit mostly in infrared or ultraviolet don't register as strongly. Our eyes filter the universe. We're built to see a narrow slice of the electromagnetic spectrum, and everything outside that slice is invisible. Ancient astronomers didn't know they were looking through a keyhole. They thought they were seeing the whole room. Modern astronomers estimate that under perfect conditions, the darkest skies Earth can offer you might see up to 9,000 stars if you could somehow observe both hemispheres at once. But perfection is rare. Most ancient observers saw far fewer. Light from cities, dust in the air, the phase of the moon, even humidity, all of these reduce the count. Ptolemy's 1022 was probably close to what he could see from Alexandria on a typical clear night. But he wrote it down as if it were the total, the complete inventory, the final answer. Why did he stop there? Why didn't he wonder if there were more? Part of it was technological. He had no tools to see deeper, but part of it was psychological. Humans crave closure. We want the list to end. We want to say this is all of it. We can rest now. The unknown makes us uncomfortable, so we draw borders around our knowledge and call them the edges of reality. Let's talk about what happened when those borders were crossed. Fast forward to the late 16th century. A Danish astronomer named Tycho Brahe built an observatory on the island of Haven. He didn't have a telescope yet. No one did. But he had something almost as powerful: obsession. He measured the positions of stars with instruments so precise, so carefully calibrated, that his data would remain the gold standard for decades. He cataloged over 1,000 stars, refining Ptolemy's work, correcting errors, adding new entries. And in 1572, he saw something that shouldn't have existed: a new star, bright sudden blazing in the constellation Cassiopeia. It hadn't been there before. The ancients said the heavens didn't change, but here was proof they did. Tycho called it a stella nova, a new star. We now know it was a supernova, the violent death of a massive star, its light finally reaching Earth after traveling for thousands of years. But at the time, it shattered the doctrine of celestial perfection. The heavens could change, stars could appear, stars could vanish. The catalog was never going to be complete because the sky itself was unstable. Here's where the first mistake deepens into something philosophical. Ancient astronomers didn't just miscount the stars, they misunderstood what counting meant. They thought a catalog was a portrait of something static. But the universe isn't static, it's a river. By the time you finish counting, the count has already changed. Stars are born in clouds of gas and dust. Stars collapse into white dwarfs, neutron stars, black holes. The Milky Way doesn't have a fixed number of stars. It has a number that shifts every second, every moment, as fusion ignites in a new core somewhere, and a distant supernova scatters its atoms across the void. So, what can we learn from Ptolemy's mistake? What can we learn from Hipparchus, from Tycho, from every astronomer who thought they had reached the end? Maybe the act of counting isn't about arrival. It's about attention. It's about looking closely, carefully, with whatever tools you have, knowing that the next generation will see more, knowing that your count will be revised, and being okay with that. There's something humble in that realization, something freeing. You don't have to know everything, you just have to know what you can, as well as you can, and pass it forward. The ancients gave us their counts, their catalogs, their careful measurements. They were wrong, but they were also right. They were right to look up, right to wonder, right to try. And maybe that's the real lesson. The mistake isn't in the number. The mistake is in thinking the number is the point. What matters is the reaching, the looking, the slow, patient work of refining our vision, knowing we'll never see it all but trying anyway. Because that's what it means to be human beneath an infinite sky. We count what we can, we name what we find, and we wait for someone someday to show us what we missed. The ancient astronomers counted stars with their eyes and their minds. They gave us a beginning, but the story was about to change. Because in 1609, a man in Italy pointed a simple tube of glass at the heavens. And in that moment, everything we thought we knew about the number of stars dissolved like smoke. The universe was about to get so much bigger, so much stranger, so much more than anyone had dared to imagine. November 1609, Padua, Italy. A mathematics professor climbs to the top of a bell tower, carrying a leather tube about as long as his arm. Inside the tube, 2 pieces of curved glass, nothing more. He points it at the moon, and what he sees breaks his understanding of the universe. Galileo Galilei wasn't the first person to build a telescope. Dutch spectacle makers had been experimenting with lenses for years, but Galileo was the first to turn that simple arrangement of glass toward the night sky, with the intention of measuring, recording, documenting what he found. And what he found was, everything was wrong. The moon wasn't smooth. Jupiter had moons of its own. And the stars, those fixed, countable, knowable points of light, were far more numerous than anyone had ever imagined. He looked at the Milky Way, that faint band of light the ancients thought was spilled milk or a road for gods, and saw it dissolve into thousands upon thousands of individual stars, packed so densely they blurred together. In one night, the count multiplied, not by tens, not by hundreds, by magnitudes that made the old catalogs look like children's sketches. This was the first great shock of the telescope. Not that it showed us new things, but that it revealed how much we'd been missing, how much the universe had been hiding in plain sight, waiting for us to sharpen our vision just a little. Let's stay with Galileo for a moment. In early 1610, he published a small book called Sidereus Nuncius, the Starry Messenger. In it, he described what he had seen through his telescope: the moons of Jupiter, the phases of Venus, the mountains and craters of our moon. But what shook the scientific community most wasn't the planets. It was the stars. Galileo wrote that wherever he pointed his telescope, new stars appeared. Stars invisible to the naked eye suddenly blazed into view. He estimated he could see 10 times as many stars through the telescope as he could without it. And his telescope wasn't even that powerful. It magnified about 20 times, barely more than a good pair of modern binoculars. Here's what that meant. If the naked eye could see roughly 6,000 stars total from both hemispheres, Galileo's telescope pushed that number to 60,000, maybe more. The universe hadn't grown. Our ability to see it had. And with that new sight came a kind of vertigo. If a simple tube of glass could reveal 10 times more stars, what else were we missing? What would we see with better glass, stronger lenses, sharper focus? The answer came slowly over centuries as telescopes grew larger, more refined, more hungry for light. But the cultural shock was immediate. For over 1,000 years, people had believed Ptolemy's count. 1,000 stars, maybe a few more. The sky was known, finite, manageable. Galileo shattered that comfort. He showed that the universe was far deeper, far more crowded, far stranger than anyone had prepared for. And he did it with a tool so simple a child could understand it. 2 pieces of glass. That's all it took to rewrite the heavens. Let's jump forward to the late 18th century. England. A man named William Herschel is obsessed with stars, not just looking at them, counting them, cataloging them, measuring them. Herschel was a musician by training, but astronomy consumed him. He built his own telescopes, grinding mirrors by hand, polishing them to near perfection. And then he did something almost maniacal. He decided to count every star he could see, not estimate, count, one by one, night after night. Herschel would sit at his telescope for hours, sometimes 8 or 10 hours straight, calling out stars to his sister Caroline, who sat nearby with pen and paper, recording every observation. They worked in the cold and the dark, barely speaking, except to note positions and magnitudes. Caroline became one of the first professional female astronomers, though history often forgets her name. She discovered 8 comets on her own and cataloged over 2,500 nebulae and star clusters. But her brother's obsession was the count, the great star count. Herschel's method was systematic. He divided the sky into sections and swept through each one, logging every star bright enough to register. By the end of his life, he and Caroline had cataloged over 90,000 stars. 90,000. That's nearly 90 times Ptolemy's original count. And Herschel knew he still wasn't seeing them all. He could see deeper than Galileo, but the faint stars, the red dwarfs, the distant giants cloaked in dust, those remained invisible. His catalog was the most complete ever made at the time, and it was still just a sketch. Here's the thing about William Herschel. He didn't just count stars. He thought about what the count meant. He realized that stars weren't evenly distributed across the sky. Some regions were dense with them, others were sparse. He began to suspect that stars weren't scattered randomly, but organized into a structure, a shape. He called it the Milky Way system, and he guessed correctly that we were inside it, looking out from within. He even tried to map it, sketching a rough outline based on star density. His map was wrong in the details, but right in the spirit. The Milky Way wasn't just a collection of stars. It was an architecture, a galaxy, and we were embedded in it like a single cell in a vast organism. But even Herschel made mistakes. He assumed that all stars had roughly the same intrinsic brightness, so a dim star must be far away and a bright star must be close. This wasn't true. Stars vary wildly in luminosity. But he didn't know that yet. No one did. So his distance estimates were off sometimes by enormous factors. Still, the attempt mattered. He was reaching for structure, trying to move beyond mere counting into understanding. Now, let's talk about a different kind of mistake, the mistake of confusion. In the 18th and early 19th centuries, astronomers kept seeing fuzzy patches in the sky, blurs, smudges. They didn't look like stars, they looked like clouds. A French astronomer named Charles Messier was hunting for comets, and these fuzzy objects kept tricking him. He'd spot a blur, get excited, then realize it wasn't moving. Comets move, these didn't. So Messier did something practical. He made a list of all the fuzzy, non-moving objects he found, so other comet hunters wouldn't waste time on them. He cataloged 110 of these objects. We now call it the Messier Catalog, M1, M31, M42. Astronomers still use these designations today. But here's the mistake. Messier thought these fuzzy patches were just nebulae clouds of gas and dust within the Milky Way. He didn't realize that some of them were entire galaxies' islands of billions of stars sitting millions of light years away. His catalog mixed together star clusters, planetary nebulae, supernova remnants, and galaxies all under the label, annoying things that aren't comets. He was cataloging some of the most profound objects in the universe and didn't know it. M31, for example, is the Andromeda Galaxy, the nearest large spiral galaxy to our own. Messier saw it as a blur. We now know it contains roughly 1 trillion stars. 1 trillion. And he listed it as object number 31 on his list of distractions. This is what happens when tools outpace understanding. The telescope showed astronomers more than they could interpret. They saw structure, but couldn't explain it. They saw variety, but couldn't categorize it. The sky was no longer simple. It was layered complex, full of objects that didn't fit into old frameworks. And the star count, that straightforward question, how many stars are there, became tangled in a deeper question, what even counts as a star? Let's talk about the evolution of the telescope itself. Galileo's first telescope used a convex objective lens and a concave eyepiece. It worked, but the field of view was narrow and the images were dim. Johannes Kepler improved the design using 2 convex lenses, which brightened the image and widened the view. Then came the reflecting telescope pioneered by Isaac Newton, which used mirrors instead of lenses. Mirrors could be made larger than lenses without the same problems of distortion and chromatic aberration. Herschel used reflecting telescopes, some with mirrors over 1 meter wide. Each improvement in design meant more light, gathered more faint stars, revealed more depth unlocked. By the 19th century, telescopes were massive. The Leviathan of Parsonstown, built in Ireland in 1845, had a mirror 6 feet across. It was the largest telescope in the world for over 70 years. With it, astronomers could see spiral structure in some nebulae, though they didn't yet understand what spirals meant. The count of visible stars climbed into the hundreds of thousands. And still, it wasn't complete. Still, the faintest stars eluded capture. Here's a question for you. Have you ever looked through a telescope, even a small one? If you have, you know that moment when something shifts, when a blur becomes a ring, when a point becomes a disk, when the thing you thought you understood reveals a hidden layer. That's what every advance in telescope design did for astronomy. It turned blurs into clarity. It turned guesses into measurements. And with each turn of clarity, the universe grew. But clarity brought new problems. The more stars astronomers saw, the harder it became to organize them. How do you catalog hundreds of thousands of stars? How do you track their positions, measure their brightnesses, record their spectra? Photography helped. In the late 19th century, astronomers began using photographic plates to capture images of the sky. A single long exposure could record thousands of stars at once, far more than a human eye could log in a night of observation. The Harvard College Observatory launched a project to photograph and catalog the entire sky. Teams of women, often called computers, analyzed the plates, measuring star positions and classifying spectra. Henrietta Swan, Leavitt, Annie Jump, Cannon, Williamina, Fleming. These women processed hundreds of thousands of stars, creating catalogs that astronomers still rely on today. And yet, even with photography, even with teams of people working for decades, the count remained incomplete. Because the Milky Way is vast, and most of it is hidden behind dust, hidden by distance, hidden in wavelengths our eyes and early instruments couldn't detect. The visible light count the stars we could see with optical telescopes reached into the millions. But that was still just the bright ones, the accessible ones. The universe was holding back. Every tool teaches us how blind we were before it. The naked eye taught us there were thousands of stars. The telescope taught us there were hundreds of thousands, then millions. And each time the lesson was the same, we'd been undercounting. We'd been seeing only what our tools allowed, and the universe, patient and vast, waited for us to build better eyes. So where does this leave us with glass and mirrors, with catalogs and photographs? We pushed the count higher and higher. But we were still inside the mystery, still looking out from within the Milky Way, trying to measure it from the inside. And that's where the next leap had to come. Not just better tools, but better understanding. We needed to know what the Milky Way actually was. Not just a collection of stars, but a structure, a shape, a galaxy with edges and a center and arms spiraling outward. We needed to stop counting and start seeing. And that shift from number to form is where we're headed now. Imagine you're inside a forest. Trees surround you in every direction. Thick trunks, dense canopy shadows layered on shadows. Now, someone asks you, what shape is this forest? Is it circular, rectangular? Does it have edges? Where's the center? You can't answer. You're inside it. You can only see the trees nearest to you. The structure is invisible from within. That's our situation with the Milky Way. We live inside it. We're embedded in its disk, surrounded by its stars, trying to map a shape we can't step outside of to see. For thousands of years, humans looked up at that pale band of light stretching across the night sky and told stories. The Greeks said it was milk sprayed from the breast of Hera. The Chinese called it the Silver River. The Norse thought it was the path souls took to the afterlife. Beautiful stories, poetic explanations, all of them wrong. The truth was quieter, stranger, and it took glass to reveal it. When Galileo pointed his telescope at the Milky Way in 1610, he saw what no one had seen before. That faint glowing band wasn't mist or vapor or divine milk. It was stars, countless stars, so many packed so closely that their individual lights blurred together into a soft glow. He wrote about it in careful, almost reverent terms, describing how the telescope dissolved the mystery into multitudes. What had seemed singular was plural. What had seemed smooth was granular. The Milky Way was made of the same stuff as the individual stars scattered across the rest of the sky. It was just denser, richer, a river of light formed by an ocean of suns. But knowing what the Milky Way was made of didn't answer the deeper question. What is it? Not just what fills it, but what shape does it take? How big is it? Where does it begin and end? And most importantly for our journey tonight, how many stars does it actually contain? The name Milky Way stuck even after we understood it wasn't milk. Language has inertia. We still call it the Milky Way. In English, the Via Lactea, in Latin names, rooted in that old myth of spilled milk. Other cultures kept their own names. In Japan, it's Amanogawa, the river of heaven. In Finland, Linnunrata, the path of birds. Each name reflects a different way of seeing a different story, told to explain that pale stripe crossing the dark. But beneath all the names, beneath all the myths, the same structure waited. A spiral galaxy. Our home. A disk of stars, gas and dust, rotating slowly around a center we couldn't yet see. It wasn't until the 20th century that astronomers began to understand the Milky Way's true structure. And the key wasn't just better telescopes. It was patience, measurement, and the willingness to accept that we're not at the center of anything. Let's talk about Harlow Shapley. In the 1910s, Shapley was studying globular clusters, dense balls of ancient stars that orbit the Milky Way like moons around a planet. He measured the distances to these clusters using a technique involving variable stars that pulse in brightness at predictable intervals. By mapping where these globular clusters were in space, Shapley noticed something strange. They weren't evenly distributed around us. They clustered in one direction toward the constellation Sagittarius. If the globular clusters orbited the center of the Milky Way and they were all concentrated in one region, then that region must be the center. And we, Earth, our sun, our local neighborhood of stars, we weren't at the center. We were out in the suburbs, about 26,000 light years from the core. This was a shock, not as dramatic as Copernicus removing Earth from the center of the solar system, but similar in spirit. We weren't special. We weren't central. We were just another star in a vast structure orbiting a center we couldn't even see because dust blocked the view. The core of the Milky Way is hidden from us in visible light. Thick clouds of interstellar dust absorb and scatter the light from the billions of stars packed into the galaxy's heart. If you look towards Sagittarius on a dark night, you'll see stars, but you won't see the center. It's veiled, obscured, waiting for infrared and radio telescopes to peel back the layers. So, what does the Milky Way actually look like? Picture a spiral. Not a perfect spiral, but a loose dynamic one, with 4 major arms curving outward from the center. The Milky Way is a barred spiral galaxy, meaning it has a central bar-shaped structure made of stars, and from the ends of that bar spiral, arms extend. These arms aren't solid. They're not like the arms of a starfish. They're density waves regions where stars and gas clump together more thickly. Stars drift in and out of the arms as they orbit like cars moving through a traffic jam. The jam stays in place, but the cars flow through. We live in one of the smaller arms called the Orion Arm, or sometimes the Orion Spur. It's a minor branch between 2 larger arms, the Perseus Arm and the Sagittarius Arm. Our sun takes about 225 million years to complete one orbit around the galactic center. The last time we were in this exact spot in our orbit, dinosaurs were just beginning to rise. The Milky Way rotates but slowly, patiently, on timescales that dwarf human history. The galaxy's disk is roughly 100,000 light years across. If you could shrink the Milky Way down so that it fit on a dinner plate, our solar system would be smaller than a single grain of sand, sitting about 2/3 of the way from the center to the edge. And the thickness of the disk, maybe 1,000 light years at most. It's thin, flat, like a pancake or a vinyl record. Stars cluster in the disk, but above and below it the density drops off sharply. Venture too far above or below the galactic plane, and you'd find yourself in the halo, a sparse region dotted with ancient globular clusters and rogue stars. Now, let's talk about what sits at the center. For a long time, astronomers suspected there was something massive there, something with enough gravity to hold the entire galaxy together as it rotated. In the 1970s, radio astronomers detected a strong radio source at the galactic core. They called it Sagittarius A, and later, as they refined their measurements, Sagittarius A star or Sagittarius A Furrow. For decades, they studied it, watching stars near it whip around at incredible speeds, their orbits dictated by something invisible and enormously heavy. In 2020, the Physics Nobel Prize went to Andrea Ghez and Reinhard Genzel for their work, proving what that something was: a supermassive black hole, 4 million times the mass of our sun, sitting at the very heart of the Milky Way, silent and unseen, invisible light, but undeniably there. Every large galaxy seems to have one, a supermassive black hole at the center, and the mass of the black hole correlates with the mass of the galaxy. It's as if the black hole and the galaxy grew up together, shaping each other. The black hole feeds on gas and stars that wander too close. The galaxy, in turn, is held together by the black hole's immense gravity. It's a symbiotic relationship written in warped space-time. But even knowing the structure, even understanding the shape, we still face the central question. How many stars are in this spiral? How do you count something so vast, so layered, so hidden by dust and distance? Here's the challenge. The Milky Way isn't uniform. The center is packed with stars, billions of them, crammed into a relatively small volume. The spiral arms are dense compared to the space between them. The halo is sparse, just ancient clusters and scattered wanderers. And then there's the dark matter, the invisible mass that makes up most of the galaxy's weight, but doesn't emit light. Dark matter doesn't count toward the star tally, but it affects how stars move, how the galaxy holds its shape. It's there, always there, a hidden framework we infer but cannot see. Astronomers use statistical methods to estimate the star count. They observe small sections of the sky, count the stars in those sections, then extrapolate to the whole galaxy. They measure the total luminosity of the Milky Way, the total light output, and divide by the average luminosity of a star. But what's the average star's range from tiny red dwarfs barely glowing to massive blue giants blazing with the light of a million suns? The distribution isn't even. Red dwarfs are the most common, making up about 70 to 80% of all stars. But they're so dim that even our nearest red dwarf neighbors are invisible to the naked eye. Then there are the stars we can't see at all. Brown dwarfs, failed stars, objects that started to form like stars but never gathered enough mass to ignite sustained fusion in their cores. They glow faintly from leftover heat, radiating in infrared, but they're incredibly hard to detect. Should we count them? They're not technically stars, but they're not planets either. They exist in a gray zone, and depending on how you define star, the count changes. Here's another complication. Stars are born in clusters and vast clouds of gas called stellar nurseries. The Orion Nebula, visible to the naked eye as a fuzzy patch in Orion's sword, is one of the closest star-forming regions to Earth. Inside it, hundreds of young stars are being born right now, condensing out of swirling gas and dust. Some of these protostars are still hidden, wrapped in cocoons of material. Are they stars yet? When does a collapsing cloud become a star? When fusion begins, when the cocoon clears. The boundaries are blurry, and stars die. They don't last forever. Massive stars explode as supernovae, scattering their atoms across space. Medium-sized stars like our sun swell into red giants, then shed their outer layers, leaving behind white dwarfs, dense cores no bigger than Earth, but containing a star's worth of mass. The smallest stars, the red dwarfs, can burn for trillions of years, far longer than the current age of the universe. None have died yet. They're all still here, faintly glowing, patient and enduring. But eventually they'll fade too. So, the number of stars in the Milky Way isn't static, it's dynamic. Stars are born. Stars die. The count shifts every moment. Right now, the Milky Way is forming new stars at a rate of about 1 to 3 solar masses per year. That's roughly 1 to 3 new stars, depending on their size. Meanwhile, stars are dying. Old giants collapsing, supernovae flashing, the galaxy breathes, inhales gas, exhales light, and the total count drifts, never quite settling. The best current estimate is somewhere between 100 billion and 400 billion stars. That's a huge range, a factor of 4. Imagine trying to count the grains of sand on a beach, but you're standing in the middle of the beach, and most of the grains are buried, and some are so small you can't see them, and new grains are washing in while old ones wash out. That's what counting the Milky Way's stars feels like. Why can't we pin it down more precisely? Because we can't see most of them. The faint ones hide. The distant ones blur together. The ones behind dust vanish entirely. We make models. We use what we can see to infer what we can't. We compare the Milky Way to other galaxies we can observe from the outside, like Andromeda, and we extrapolate. But models are approximations, useful but not exact. What we do know is this: the Milky Way is old, about 13 billion years, almost as old as the universe itself. It's been making stars for most of that time, and it's been colliding with smaller galaxies, cannibalizing them, pulling in their stars, and adding them to the total. The Sagittarius dwarf elliptical galaxy is currently being torn apart by the Milky Way's gravity, its stars streaming into ours. In a few billion years, the Milky Way will collide with Andromeda, and the two will merge into a larger elliptical galaxy. The star count will double at least, but by then, the sun will be gone, Earth will be gone, and there won't be anyone left here to update the catalog. We live inside a story we can't fully read, a structure we can't fully see. And maybe that's fitting. Maybe being inside the mystery is the point. We measure what we can, we map what we reach, and we accept that some answers will always be incomplete. Not because we're lazy or incapable, but because we're embedded. We're part of the thing we're trying to understand. And that changes the question from, how many stars are there, to, how do we live with not knowing? But we're not done counting yet. Because even if we can't see all the stars directly, we found ways to measure them indirectly, ways to weigh the galaxy, ways to track its motion, ways to use mathematics and physics to fill in the gaps our eyes can't reach. And that's where we'll turn now, to the methods, the surveys, the missions that have pushed us closer to an answer, even if the answer keeps shifting just out of reach. How do you count something you can't see all of? How do you measure something too vast to hold in a single frame? The answer lies not in seeing everything, but in seeing enough, carefully, precisely, and then letting mathematics do what human eyes cannot. This is the art of the star survey, a patient, methodical effort to sample the sky, measure what's measurable, and extrapolate the rest. It's like trying to understand an entire forest by studying a single acre. You count the trees in that acre, note their types, measure their spacing, and from that small patch, you infer the whole. It's not perfect, but it's the best we can do when the thing we're measuring is 100,000 light years wide and we're stuck inside it. Let's start with the idea of statistical sampling. You don't need to count every star to know how many there are. You just need to count enough stars in enough different regions to establish a pattern. If you observe 10 small patches of sky scattered across different parts of the Milky Way, and you find an average of 1,000 stars per patch, you can multiply that by the total number of patches the sky contains. The math is simple. The execution is not. Because the Milky Way isn't uniform, some patches are dense with stars, others are nearly empty. The challenge is choosing which patches to observe and making sure your sample represents the whole. This is what modern star surveys do. They divide the sky into grids, observe each section with powerful telescopes, and compile the data into catalogs. The goal isn't just to count stars, but to measure their positions, brightnesses, colors, distances, and motions. Every data point refines the picture. Every measurement tightens the estimate. One of the largest and most ambitious star surveys ever conducted is called Gaia. Named after the Greek goddess of Earth, Gaia is a space telescope launched by the European Space Agency in 2013. Its mission is simple in concept. Staggering in scale, measure the positions and motions of over 1 billion stars with unprecedented precision. 1 billion. That's less than 1% of the Milky Way's total star count, but it's the most detailed, most accurate sample we've ever gathered. Gaia orbits the Sun at a point called L2, about 1 million miles from Earth, where it has an unobstructed view of the sky. It spins slowly, scanning the heavens, measuring each star multiple times over the course of years. By comparing these measurements, Gaia can detect tiny shifts in a star's position. Shifts caused by parallax, the apparent motion of a star against the distant background as Earth orbits the Sun. Parallax is one of the most reliable ways to measure stellar distances, and Gaia does it with extraordinary precision. It can measure angles smaller than the width of a human hair, seen from 1,000 miles away. Why does this matter? Because knowing a star's distance unlocks everything else. If you know how far away a star is, you can calculate its true brightness, its size, its mass. You can trace its motion through space. You can place it in the three-dimensional structure of the galaxy. Gaia has given us the most detailed map of the Milky Way ever made, not just a flat picture, but a layered dynamic model showing how stars move where they cluster, how the spiral arms curve and flow. But Gaia is just one piece of the puzzle. Before Gaia, there was the 2-micron all-sky survey, or 2MOS, which observed the sky in infrared light. Infrared can penetrate dust that blocks visible light, revealing stars hidden in the galactic core and in dense nebulae. 2MASS cataloged over 300 million stars and other objects, giving astronomers a heat map of the Milky Way. Then there's the Sloan Digital Sky Survey, or SDSS, which has been mapping the universe since 2000, cataloging hundreds of millions of stars and galaxies, measuring their spectra, building a database so vast it takes teams of researchers years to analyze. Each survey adds a layer. Each one sees something the others miss. Optical surveys see bright stars. Infrared surveys see cool stars and protostars. Radio surveys detect the gas clouds where stars form. Ultraviolet surveys catch the hottest, most massive stars, the ones burning so fiercely they'll explode as supernovae within a few million years. Piece by piece, wavelength by wavelength, the picture comes together. Now, let's talk about parallax in a little more detail, because it's one of the oldest and most elegant methods we have for measuring distance. Hold your finger up in front of your face. Close one eye, then the other. Your finger appears to shift against the background. That shift is parallax. The closer your finger is to your face, the larger the shift. The same principle works for stars. As Earth orbits the Sun, our viewpoint changes. Nearby, stars appear to shift slightly against the backdrop of more distant stars. By measuring that shift, we can calculate how far away the star is. The problem is, even the nearest stars are so far away that their parallax shifts are incredibly tiny. The closest star system, Alpha Centauri, is about 4.37 light-years away. Its parallax shift is less than 1 arc-second, roughly the angle you'd see if you looked at a dime from 2 miles away. Before space telescopes, ground-based observations could only measure parallax out to a few hundred light-years with any accuracy. Gaia extends that range to tens of thousands of light-years, reaching deep into the Milky Way's disk. But even Gaia has limits. Beyond a certain distance, parallax becomes too small to measure reliably. For the farthest stars, astronomers use other methods. Standard candles, stars, with known intrinsic brightness, like Cepheid variables. These stars pulse in a predictable way, and the period of their pulsing correlates with their luminosity. Measure the pulse, and you know how bright the star truly is. Compare that to how bright it appears, and you can calculate the distance. It's indirect, but it works. Another method involves spectroscopy, analyzing the light from a star to determine its temperature composition and motion. Every element emits light at specific wavelengths, like a fingerprint. By reading those fingerprints, astronomers can tell what a star is made of, how hot it burns, and whether it's moving toward us or away from us. If a star is moving away, its light shifts toward the red end of the spectrum redshift. If it's moving toward us, the light shifts blue. This Doppler effect, the same phenomenon that makes a passing ambulance siren change pitch, lets us measure stellar velocities with remarkable precision. Gaia doesn't just measure positions, it measures motions. Every star in the galaxy is moving, orbiting the galactic center, drifting through local space. Some stars move in tight groups born together in the same cloud, still traveling as a cluster. Others are runaways ejected from their birthplaces by gravitational interactions or supernova explosions, now wandering alone through the void. By tracking these motions, Gaia helps us understand the Milky Way's dynamics, how it rotates, how its spiral arms form and dissolve, how stars migrate from the inner regions to the outer edges over billions of years. Let's talk about star classification for a moment. Not all stars are the same. Astronomers sort them by spectral type A system based on temperature and color. The sequence goes O, B, A, F, G, K, M from hottest to coolest. O-type stars are blue, blazing with surface temperatures over 30,000 Kelvin. M-type stars are red, cool, dim, with temperatures around 3,000 Kelvin. Our Sun is a G-type star, middling in temperature to yellow-white, neither the hottest nor the coolest. Most stars are M-type, the red dwarfs, small, faint, long-lived. They make up the majority of the Milky Way's population, but they're so dim that even with telescopes, they're hard to see at any great distance. Then there's the Hertzsprung-Russell diagram, a chart that plots stars by their luminosity and temperature. Most stars fall along a diagonal band called the main sequence, where they spend the majority of their lives fusing hydrogen into helium. But some stars stray from the sequence. Giants and supergiants sit in the upper right, cool but incredibly luminous because they're so large. White dwarfs huddle in the lower left, hot but faint because they're so small. The HR diagram is a map of stellar life cycles, showing not just what stars are, but where they are in their journey from birth to death. Understanding these classifications helps with the count. If you know what type of star you're looking at, you can estimate its mass, its lifespan, its brightness. You can infer how many similar stars might exist in regions you can't observe directly. It's like identifying tree species in that forest sample. Once you know the ratio of oaks to pines to maples, you can guess the composition of the entire forest. But here's the complication. Not everything that looks like a star is a star. Brown dwarfs, those failed stars we mentioned earlier, glow faintly in infrared, but never ignite true fusion. They're more massive than planets, less massive than stars. Should they count? Astronomers debate this. Some catalogs include them, others don't. The definition of star gets fuzzy at the edges. And then there's dark matter, the invisible mass that makes up about 85% of the matter in the universe. We can't see it. It doesn't emit light. It doesn't interact with electromagnetic radiation. But we know it's there because of its gravitational effects. Stars orbit the Milky Way faster than they should, based on the visible mass alone. The galaxy holds together more tightly than the mass of stars' gas and dust can account for. Something else is there, something massive, something dark. It doesn't add to the star count, but it shapes the galaxy's structure, influences how stars move, dictates the very architecture we're trying to measure. Dark matter is the scaffolding. Stars are the decoration. We count the decoration and infer the scaffolding from how the decoration is arranged. It's backwards indirect, but it's all we have. We can't see the dark matter, so we look for its fingerprints in the motion of what we can see. Surveys also reveal the Milky Way's birth rate. How many new stars form each year? Current estimates suggest about 1 to 3 solar masses worth of new stars annually. That might sound like a lot, but compared to the total mass of the galaxy, it's slow. The Milky Way is an old, mature galaxy. Its star-forming days are mostly behind it. Young galaxies in the early universe formed stars at rates hundreds of times faster. They were furnaces burning through their gas supplies, lighting up with brilliant blue stars that lived fast and died young. The Milky Way has settled. It still makes stars, but quietly, methodically in pockets where gas clouds collapse under their own gravity. The Orion Nebula is one of those pockets. About 1,300 light-years away, glowing faintly to the naked eye, blazing in telescope images. Inside it, hundreds of young stars, many still wrapped in disks of gas and dust. Planetary systems in the making. Observing regions like Orion helps astronomers understand the star formation process, how often it happens, under what conditions, and how many stars result from each collapsing cloud. And stars don't form alone. They tend to form in clusters. Open clusters like the Pleiades are loose groups of young stars born together, still drifting through space as a family. Globular clusters are much older, denser, tightly packed balls of hundreds of thousands of stars, all roughly the same age, orbiting the Milky Way like ancient satellites. These clusters are fossils, remnants from the galaxy's early days, and studying them gives us clues about the Milky Way's formation and evolution. By counting stars in clusters, measuring their ages, tracking their chemical compositions, astronomers build a timeline. They can tell which stars formed first, which came later, how the galaxy has changed over billions of years. The oldest stars are metal-poor, formed before the universe had time to create heavy elements through supernova explosions. The youngest stars are metal-rich, built from the ashes of earlier generations. Each star carries a story written in its spectrum, and reading those stories one by one lets us reconstruct the Milky Way's history. So when we ask how many stars are in the Milky Way, we're not just asking for a number. We're asking about structure, composition, and history motion. We're asking how the galaxy breathes, how it grows, how it recycles its material. The count is part of a larger story, a story that spans 13 billion years and will continue for trillions more. The tools keep improving, the surveys keep expanding, and the estimate keeps refining. We've gone from Ptolemy's 1,000 to modern estimates of hundreds of billions, and we're still not finished. Because every time we look deeper, we find more faint stars, more hidden clusters, more complexity in the spiral arms. The Milky Way gives up its secrets slowly, piece by piece, and we're learning to be patient. But numbers alone don't capture it. You can say 100 billion stars or 400 billion stars, and the numbers feel abstract, disconnected from experience. What does 100 billion even mean? How do you hold that in your mind? Maybe you can't. Maybe that's the point. Maybe the count isn't meant to be graspable. It's meant to remind us of scale of vastness, of the sheer improbability that we're here at all. Thinking these thoughts, asking these questions, reaching for answers will never fully hold. And yet, we reach anyway. We build telescopes. We launch satellites. We write algorithms to process data. We measure parallax shifts smaller than the width of an atom seen from across a city. We do this because counting stars is more than a task. It's an act of attention. It's a way of saying, you matter. Each one of you, even the faint ones, even the ones we'll never name. The count is always incomplete. The methods are always improving. And somewhere in the quiet background of all this careful science is a simple truth. We're embedded in a galaxy we're trying to understand, using tools made of atoms that were once inside stars. We're stardust counting stars. And maybe that's enough. Maybe the reaching is the answer. But we're not done yet. Because the number we've been chasing, that 100 to 400 billion, it comes with a caveat. It comes with the word estimate. And estimates have margins of error. They have assumptions. They have gaps. So let's look at why the number is still so uncertain, why it shifts depending on what you count and why. In the end, the final answer might always be just out of reach. 100 billion stars, or maybe 400 billion, possibly somewhere in between. The range is enormous, and that should tell you something. After centuries of telescopes, decades of satellites, years of processing data from billions of measurements, we still can't pin down the exact number of stars in our own galaxy. Not even close. Why? Because the question itself keeps shifting. Every time we refine our tools, we discover we were undercounting. Every time we adjust our definitions, the number changes. And beneath it all lies a deeper truth. The Milky Way isn't a static object frozen in time. It's alive in its own slow cosmic way. Stars are born, stars die, and the count never stops moving. Let's start with the estimate itself. 100 to 400 billion stars. That's a range of 300 billion. Imagine if someone asked you how much money you had in your bank account, and you said somewhere between $100 and $400. You'd sound uncertain, maybe careless. But this isn't carelessness, it's honesty. It's an admission that the thing we're trying to measure is almost impossibly complex, layered with variables we can't fully control. So, what accounts for the range part of it is observational limits. We can't see every star. Dust blocks our view of large portions of the galaxy, especially toward the center. Thick clouds of interstellar material absorb visible light, hiding billions of stars from optical telescopes. Infrared can penetrate some of that dust, but not all of it. Radio waves pass through even more, but they don't show us individual stars, just the gas and magnetic fields around them. We're piecing together a picture from incomplete data, like trying to reconstruct a painting when half the canvas is covered. Then there's the problem of faint stars. Red dwarfs are the most common stars in the galaxy, making up about 70 to 80% of the total population. But they're dim. So dim that even nearby red dwarfs are invisible to the naked eye. Proxima Centauri, the closest star to our solar system after the Sun, is a red dwarf. It's only 4.24 light-years away, practically next door in cosmic terms, and you can't see it without a telescope. If the nearest star is invisible, how many distant red dwarfs are we missing? Millions, billions. The count depends on assumptions about how many faint stars exist in regions we can't observe directly. And then there's the question of what counts as a star. Brown dwarfs sit in a gray zone. They're more massive than planets, but not massive enough to sustain hydrogen fusion, the defining process of a true star. They glow faintly from residual heat, radiating mostly in infrared, but they never truly ignite. Are they stars? Depends on who you ask. Some catalogs include them, others don't. If you count brown dwarfs, the number goes up. If you exclude them, it goes down. The boundary isn't clear, and the count shifts depending on where you draw the line. Let's talk about stellar nurseries. Stars don't appear fully formed. They condense out of clouds of gas and dust regions called molecular clouds, where gravity pulls material together until the core gets hot enough and dense enough for fusion to begin. The Eagle Nebula, made famous by the Hubble Space Telescope's Pillars of Creation image, is one such nursery. Inside those towering columns of gas stars are being born right now, but many of them are still hidden, wrapped in thick cocoons of dust. They're protostars, not quite stars yet, but on their way. Do we count them? At what point does a collapsing cloud become a star? When fusion starts, when the surrounding material clears enough to let light escape. The definition matters, and it changes the total. The Milky Way forms new stars at a rate of about 1 to 3 solar masses per year. That might not sound like much, but over millions of years it adds up. In the time humans have existed as a species, roughly 300,000 years, the Milky Way has created somewhere between 300,000 and 900,000 new stars. Meanwhile, stars have been dying. Massive stars explode as supernovae, scattering their material back into space. Medium-sized stars like our Sun swell into red giants, shed their outer layers, and leave behind white dwarfs. The smallest stars, red dwarfs, live so long that none have died yet. The universe isn't old enough, but eventually even they'll fade. So the number isn't fixed, it's dynamic. The Milky Way breathes in, gas exhales stars, and the total population shifts every moment. When we say, how many stars are there, we're really asking, how many stars are there right now? And by the time we finish the sentence, the answer has already changed. Let's dig into another complication: stellar remnants. When a star dies, it doesn't always vanish. Massive stars explode and leave behind neutron stars, or black holes, objects so dense that a sugar cube-sized piece would weigh as much as all of humanity combined. Medium stars leave white dwarfs, Earth-sized embers still glowing from leftover heat. These remnants don't fuse hydrogen. They're not technically stars anymore, but they were stars. And they're still out there scattered through the galaxy, silent and invisible, unless they happen to be accreting matter or emitting radiation we can detect. Do we count them? Most surveys don't, but they're part of the story, part of the galaxy's total stellar history. Then there's the problem of distance. The farther away a star is, the harder it is to see. Brightness falls off with the square of distance, so a star that's twice as far away appears 4 times dimmer. A star 10 times farther appears 100 times dimmer. Beyond a certain distance, even large stars fade below the detection threshold of our instruments. We know they're there statistically. We can infer their presence from the overall luminosity of distant regions. But we can't count them individually. We have to estimate. Astronomers use something called the initial mass function, or IMF, a statistical model that describes the distribution of stellar masses at birth. The IMF tells us that for every massive bright star, there are hundreds of smaller, dimmer ones. By counting the bright stars we can see and applying the IMF, we estimate how many faint stars are hiding in the same region. It's a model. A good model tested against observations, but still a model. And models have uncertainties. Different parts of the galaxy have different star densities. The core is packed. The spiral arms are dense. The halo is sparse. If you average the density across the entire galaxy, you'd get a number that doesn't reflect any single location accurately. So, astronomers divide the galaxy into zones, estimate the star count in each zone, and add them up. But the boundaries between zones are fuzzy. The density gradients are smooth, not sharp. Every division introduces a margin of error. Let's compare the Milky Way to Andromeda, the nearest large galaxy. Andromeda is about 2.5 million light-years away, close enough that we can study it in detail. Because we're outside it, we can see its full structure. We can measure its total light output, its mass, its rotation. And from those measurements, astronomers estimate Andromeda contains about 1 trillion stars. 1 trillion. That's roughly 2 to 10 times the Milky Way's count, depending on which estimate you use. Andromeda is bigger, more massive, more luminous. But it's the same type of galaxy, a barred spiral, similar in structure. By comparing the two, we refine our understanding of how many stars a galaxy like ours should hold. In a few billion years, the Milky Way and Andromeda will collide. Not a violent crash, but a slow gravitational dance. The stars are so far apart that actual collisions between them will be rare. But the galaxies will merge their stars, mingling their gas clouds, compressing and triggering bursts of new star formation. The combined galaxy, sometimes called Milkomeda, will be an elliptical giant containing somewhere between 1 and 1.5 trillion stars. The count will double, maybe triple. But by then, the sun will have swelled into a red giant, likely consuming Earth. There won't be anyone here to update the catalog. Now, let's talk about what we can't see at all. Dark matter. It doesn't emit light, doesn't absorb light, doesn't interact with electromagnetic radiation in any way we can detect. But it's there. We know because of gravity. Stars in the outer regions of the Milky Way orbit faster than they should, based on the visible mass. The galaxy holds together more tightly than the mass of stars, gas, and dust can account for. Something invisible is adding weight, shaping the galaxy's structure, dictating how stars move. Dark matter makes up about 85% of the matter in the universe, but it doesn't contribute to the star count. It's the stage, not the actors. We count the actors and infer the stage from how they're arranged. There's also dark energy, the mysterious force driving the universe's accelerated expansion. It doesn't affect the Milky Way's star count directly, but it shapes the larger cosmic context. Galaxies are moving apart. The space between them is growing. In the far future, trillions of years from now, galaxies will be so far apart that observers in one galaxy won't be able to see any others. The night sky will go dark except for the stars in their own galaxy. The universe will seem smaller, lonelier, and the count limited to a single galaxy will feel even more incomplete. But let's return to the present, to the range, 100 to 400 billion. Why such a wide gap? Because different studies use different methods, different assumptions, different data sets. Some focus on optical observations, others use infrared. Some include brown dwarfs, others don't. Some apply aggressive corrections for dust extinction. Others are more conservative. Each approach is valid, but each produces a slightly different number. And when you stack all those numbers together, the range expands. Here's a thought experiment. Imagine you're trying to count the number of people in a city, but you can't see into every building. You count the people on the streets and the parks in visible windows. Then you estimate how many are inside based on the size of the buildings, the time of day, the density of the visible population. Your count will have a range. It'll be an estimate, not an exact figure. And if someone else does the same exercise using different assumptions, they'll get a different range. That's where we are with the Milky Way. We're counting what we can see and estimating the rest. Does the uncertainty bother you? It shouldn't, because the point isn't the exact number, the point is the scale. Whether it's 100 billion or 400 billion, the message is the same. There are more stars in the Milky Way than you can comprehend, more than you can count in a lifetime, more than all the grains of sand on all the beaches of Earth by some estimates. The number is vast, and the vastness is the truth. Every star is a sun. Every sun could have planets. Every planet could have moons. And somewhere in that incomprehensible multitude might be another world like ours. Another place where beings look up at their sky and wonder how many stars there are. Another place where the count is uncertain, the range is wide, and the question keeps shifting. We're not unique in asking. We might not even be unique in existing. The count will keep changing. New surveys will launch. Better telescopes will peer deeper. Algorithms will refine the models. And the estimate will narrow, then widen again, as we discover new types of objects that blur the definitions. The Milky Way will keep forming stars, keep losing stars, keep evolving, and we'll keep counting knowing we'll never reach a final answer, but counting anyway. Because counting is how we pay attention. It's how we honor the complexity. It's how we say you're here, and we see you even if we can't see all of you. The final number is always wrong because there is no final number. There's only the latest estimate, the best guess, the most refined approximation. And maybe that's enough. Maybe the uncertainty is part of the beauty. Maybe not knowing exactly keeps us curious, keeps us looking, keeps us humble. But there's another layer to this story, another reason why the count feels incomplete. Because even the stars we know exist, even the ones we've cataloged and measured, some of them are already gone. Their light is still traveling toward us, but the stars themselves have died, collapsed, exploded, vanished. We're seeing ghosts. And that truth, that disconnect between what we see and what is, opens the door to something even stranger. The limits of light itself, the edges of time, the stars we'll never see, not because they're too faint, but because their light hasn't reached us yet, or never will. Light has a speed. That sounds obvious, almost too simple to mention. But that one fact, the finite speed of light, changes everything about how we see the universe. It means when you look at a star, you're not seeing it as it is. You're seeing it as it was. Light takes time to travel, and distance turns vision into history. The star you're looking at might already be gone, exploded, collapsed, faded into darkness. But its light is still here, still traveling, still arriving at your eye, carrying a message from the past. You're watching a ghost, a memory written in photons. And that disconnect between what we see and what exists is one of the strangest, most humbling truths about counting stars. Every star we observe is a time capsule. The farther away it is, the older the light. Proxima Centauri, the nearest star beyond our sun, is 4.24 light-years away. When you see Proxima Centauri, you're seeing light that left the star over 4 years ago. If Proxima Centauri exploded today, we wouldn't know for another 4 years. The explosion would happen, the star would vanish, but its light would keep arriving, oblivious, unchanged, until the final photons crossed the gap, and the image finally winked out. Now, stretch that idea across the galaxy. Betelgeuse, the red supergiant in Orion's shoulder, sits roughly 550 light-years away. The light you see from Betelgeuse tonight left that star around the year 1470, before Columbus crossed the Atlantic, before the printing press spread across Europe. Betelgeuse is unstable. Astronomers know it will explode as a supernova, possibly soon, possibly in the next 100,000 years. But soon in cosmic terms is meaningless. It could have already exploded 500 years ago. We just wouldn't know yet. The light from the explosion is still on its way, racing through the void, carrying news we haven't received. Here's the strange part. If Betelgeuse has already exploded, it's no longer part of the current star count. But we still see it. We still catalog it. We still measure its brightness, track its variability, analyze its spectrum. The star might be gone, but the light remains a messenger that hasn't delivered its final message. We count the light, not the star. And that gap between seeing and being is where the limits start to show. Let's think bigger. The Milky Way is about 100,000 light years across. If you could somehow take a snapshot of the entire galaxy right now, freezing every star in this exact moment, you'd see a galaxy that doesn't quite match what we observe. The stars we see near the center, 26,000 light years away, are showing us what they looked like 26,000 years ago. The stars near the edge, 50,000 light years out, are even older. They're light-carrying images from 50 millennia in the past. When we look at the Milky Way, we're not seeing a single moment. We're seeing a layered collage of different moments stitched together by the speed of light. This creates a subtle problem for counting. If a star was born 1,000 years ago, but it's 2,000 light years away, we won't see it yet. The light hasn't arrived. That star exists right now, contributing to the total count, but it's invisible to us. It's part of the galaxy's present, but not yet part of our observation. Conversely, some stars we see and count have already died. They're part of our observation, but not part of the galaxy's present. The count is always slightly out of sync with reality. The farther we look, the worse this gets. Not just in the Milky Way, but beyond it. When we observe distant galaxies millions or billions of light years away, we're seeing them as they were in the deep past. The Andromeda galaxy is 2.5 million light years away. The light we see from Andromeda left when early humans were just beginning to use stone tools. Andromeda looks different now than it did then. Stars have been born. Stars have died. The spiral arms have rotated. But we won't see those changes for another 2.5 million years. And here's where it gets even stranger. The universe is expanding. Space itself is stretching, carrying galaxies apart. The farther away a galaxy is, the faster it's moving away from us. At a certain distance, galaxies are receding so quickly that their light is redshifted into invisibility, stretched into wavelengths our instruments can't detect. And beyond that, there's a horizon, a boundary not in space, but in time and light, the edge of the observable universe. The observable universe is roughly 93 billion light years across, but the universe itself is only about 13.8 billion years old. How can something be 93 billion light years wide if light has only had 13.8 billion years to travel? Because space has been expanding the whole time. Light that left a distant galaxy 13 billion years ago has been traveling toward us ever since. But during that time, the space between us and that galaxy has stretched. The galaxy is now much farther away than it was when the light started its journey. We see the galaxy as it was 13 billion years ago. But the galaxy itself, if it still exists, is now roughly 46 billion light years away. There are galaxies beyond the observable universe, galaxies whose light will never reach us, not because the light isn't traveling, but because the expansion of space is carrying them away faster than light can close the gap. These galaxies exist. They contain stars, but we'll never see them. They're beyond the horizon, and the horizon is absolute. No telescope, no matter how powerful, can see past it. It's not a limit of technology, it's a limit of physics. Think about what that means for counting stars. Even if we could count every star in the observable universe, we'd still be missing most of the universe. Most of reality is hidden from us not by distance alone, but by the structure of space-time itself. The count is incomplete not because we're lazy or our tools are inadequate, but because some things are fundamentally unobservable. Let's bring this back to the Milky Way. Even within our own galaxy, there are stars we'll struggle to see. Not because they're beyond the horizon, but because they're cloaked, dust clouds. Molecular clouds, dense nebulae, these absorb and scatter light. The core of the Milky Way is almost completely hidden in visible wavelengths. Infrared can penetrate some of the dust, but not all. Radio waves pass through even more, but they show us gas and magnetic fields, not individual stars. We're looking through a fog, and the fog doesn't clear evenly. Then there are rogue stars, stars ejected from the galaxy by gravitational interactions, now drifting through intergalactic space alone and invisible at such vast distances. We know they exist because we've detected some in the space between galaxies, but we don't know how many. They're orphans untethered, too faint and too far to count. They were born in the Milky Way maybe, or in some other galaxy, but now they belong to no one, floating in the void, uncatalogued and uncountable. There are also stars that have simply faded beyond detection. White dwarfs, the remnants of sun-like stars, glow faintly from residual heat. Over billions of years, they cool, dimming until they're almost invisible. Eventually, they'll become black dwarfs, cold, dark, inert. The universe isn't old enough for any white dwarfs to have cooled completely, but someday, trillions of years from now, the galaxy will be full of black dwarfs, stellar corpses that don't emit light, don't interact, just sit there silent and invisible. Future astronomers, if they exist, will struggle to count them. They'll know they're there statistically, but seeing them directly will be nearly impossible. And what about neutron stars? When a massive star explodes as a supernova, the core collapses into an object so dense that a teaspoon of its material would weigh as much as a mountain. Neutron stars are small, maybe 20 kilometers across, and unless they're pulsars emitting beams of radiation, like cosmic lighthouses, they're almost impossible to detect. We know there should be millions of neutron stars in the Milky Way remnants of ancient supernovae, but we've only found a few thousand. The rest are out there dark and silent, contributing to the galaxy's mass, but not to the light invisible to most surveys. Black holes are even worse. When the most massive stars die, they collapse into black holes, objects so dense that not even light can escape their gravity. They're invisible by definition. We can only detect them indirectly by watching how they affect nearby matter, or by catching gravitational waves when they collide. The Milky Way likely contains tens of millions of black holes, stellar mass black holes scattered throughout the disk. But we've confirmed only a few dozen. The rest are hidden, lurking in the dark, impossible to count directly. Here's a question for you. If a star dies and no light escapes, was it ever really there? Philosophically, maybe not. But physically, yes. It contributes to the galaxy's mass. It warps space-time. It influences the orbits of nearby stars. It's real even if it's invisible, and that's the challenge. How do you count what you can't see? How do you catalog the dark? Astronomers do it with inference. They measure the motion of visible stars and calculate how much unseen mass is needed to explain those motions. They use gravitational lensing, watching how light from distant objects bends around invisible masses. They build models, refine estimates, test predictions. But it's all indirect. The dark objects don't announce themselves. They have to be coaxed out of the data piece by piece. And then there's the cosmic microwave background, the CMB, the faint glow of radiation left over from the Big Bang. It's the oldest light in the universe, emitted about 380,000 years after the beginning, when the universe cooled enough for atoms to form and light to travel freely for the first time. The CMB is a wall, a boundary. We can't see anything beyond it, not with light. The universe before that moment is opaque. Whatever happened in those first 380,000 years, whatever structures formed, whatever processes played out, they're hidden behind the CMB, inaccessible to observation. So, when we ask how many stars there are, we're really asking how many stars we can see or infer within the observable universe using the light that has had time to reach us. The true number, the total count of all stars and all of existence, is unknowable. It might be infinite. The universe might extend forever, containing an endless number of galaxies, an endless number of stars. Or it might be finite, but so large that the difference between very large and infinite becomes meaningless. We'll never know. The horizon limits us. Time limits us. Light itself limits us. But maybe that's okay. Maybe not knowing the total is part of the experience. Because the act of looking, the act of reaching toward the edge of the knowable, that's where meaning lives. We look up at the night sky and see a few thousand stars with our eyes. We know there are billions more we can't see. Billions more that have already died but still glow. Billions more that haven't been born yet but will be long after we're gone. And somewhere beyond all of that, there are stars we'll never see. Stars whose light will never reach us. Stars that exist in a part of the universe forever sealed off from ours. They're there, shining, burning, living their stellar lives in complete isolation from our awareness. And maybe that's the most humbling truth of all, that the universe is so vast, so layered, so rich with structure and light, that most of it will always remain a mystery. We count what we can, we marvel at what we find, and we accept that the full picture will always be just out of reach. But even the incomplete picture, even the fragment we can see, holds something powerful. Because if we've learned anything from this journey through the Milky Way, through the history of counting stars, through the tools and methods and challenges, it's this: the numbers don't matter as much as the scale. The scale doesn't matter as much as the humility. And the humility doesn't matter as much as the wonder. The stars we can't see remind us how small we are, but the stars we can see remind us we're looking. And maybe that's the point. So, where does that leave us? With light traveling through the dark, carrying messages from stars that might already be gone. With a galaxy too large to see in a single moment, too complex to count with certainty. With horizons we can't cross and limits we can't escape. But also with curiosity, with questions, with the stubborn insistence on reaching anyway, even when the answer is incomplete. And that persistence that reaching is about to take us somewhere unexpected. Not outward to more stars, but inward to what the stars mean, to what they teach us about ourselves. There are more stars in the Milky Way than grains of sand on all the beaches of Earth. That's the comparison people like to make. It sounds poetic, almost comforting in its scale. But let's sit with that for a moment. Actually sit with it. Try to imagine 100 billion grains of sand. Try to picture them scattered across every coastline, every desert, every riverbed on the planet. You can't. The number is too big. It dissolves into abstraction. And that's just our galaxy. One galaxy among hundreds of billions, maybe trillions in the observable universe. Each one filled with stars. Each star potentially circled by planets. Each planet a world with its own geology, its own weather, its own silence. The scale doesn't just humble you, it erases you. It makes you wonder if significance is even possible when the universe is this vast. In 1990, the Voyager 1 spacecraft, over 3.7 billion miles from Earth, turned its camera back toward home. At the request of astronomer Carl Sagan, it captured an image that would change how we see ourselves. Earth appeared as a single pixel, a pale blue dot barely visible against the vastness of space, suspended in a beam of scattered sunlight. Sagan later wrote about that image, describing how every human who ever lived, every war, every love story, every triumph and tragedy happened on that tiny speck of dust. He called it a reminder of our responsibility to deal kindly with one another, to preserve and cherish the pale blue dot, the only home we've ever known. That photograph is over 30 years old now, but its message hasn't faded. If anything, it's grown sharper. Because the more we learn about the universe, the smaller we become. Not smaller in importance, but smaller in proportion. We're not the center. We're not special in location. We're not even particularly common. We're an anomaly, a statistical blip, a fragile arrangement of atoms that somehow became aware of itself, looking out at a universe that doesn't seem to notice. But here's the strange thing. Being small doesn't feel like a tragedy. Not when you really let it settle. There's a kind of peace in it, a kind of freedom. If the universe is this vast, if there are hundreds of billions of stars just in our galaxy, then maybe our mistakes aren't cosmic. Maybe our failures aren't final. Maybe we're not carrying the weight of existence on our shoulders. We're just here, briefly, quietly, like a single note in an infinite symphony. let's talk about numbers for a moment. 100 billion stars in the Milky Way. But what does 100 billion actually mean in human terms? If you counted one star per second without stopping, it would take you over 3,000 years to count them all. 3,000 years. That's longer than recorded human history. You'd start counting in the Bronze Age and finish sometime in the distant future. And that's just our galaxy. Add in the rest of the observable universe and the count becomes meaningless. The numbers stop representing anything we can hold. Astronomers estimate there are about 2 trillion galaxies in the observable universe. If each galaxy contains an average of 100 billion stars, that's roughly 200 billion trillion stars total. Written out, that's a 2 followed by 23 zeros. 200 sextillion. The number is so large it loses texture. It becomes noise. And yet each one of those stars is a sun. Each one is real. Each one is burning, fusing hydrogen into helium, radiating light across the void. Now, compare that to the number of people who have ever lived on Earth. Demographers estimate about 100 billion humans have existed since our species emerged, roughly 300,000 years ago. 100 billion people. That's roughly the same as the number of stars in the Milky Way. One person, one star. It's a strange symmetry, meaningless maybe, but still strange. Here's another comparison. The atoms in your body. You're made of roughly 7 octillion atoms. That's a 7 followed by 27 zeros. More atoms in a single human body than stars in the observable universe. You are quite literally more complex internally than the night sky is externally. The universe is vast, yes, but you're not simple. You're a cosmos folded into flesh. And those atoms, they weren't always yours. Every atom in your body was forged inside a star. Hydrogen and helium from the Big Bang fused into carbon, nitrogen, oxygen, iron, all the elements that make up your bones, your blood, your brain. When those stars died, they scattered their atoms across space. Those atoms drifted through nebulae, condensed into new stars. New planets eventually found their way into the molecules that became life. You are stardust, literally, not poetically, literally. The calcium in your bones was made in a supernova. The iron in your blood came from a dying star. You're not separate from the universe. You're a piece of it, a temporary arrangement, a pattern that the cosmos made while trying out different configurations. Carl Sagan said it best: we are a way for the universe to know itself. The atoms that were once scattered, inert, unconscious have come together in such a way that they can look back at the stars they came from and wonder. That's not small, that's extraordinary. But let's not romanticize it too much, because the universe also teaches us humility. And humility isn't always comfortable. For most of human history, we thought we were the center. The Earth was the center of the cosmos. The sun and stars revolved around us. Then Copernicus said, "No, the sun is the center and we orbit it." Then we realized the sun isn't the center either. It's just one star among billions orbiting the center of the Milky Way. And the Milky Way isn't the center. It's just one galaxy among trillions. There is no center. Or, if there is, we're nowhere near it. Every step in that journey was a demotion, a humbling. And yet, paradoxically, each step also expanded our understanding. We lost our privileged position, but we gained perspective. We're not special in location, but we're special in awareness. We're the only beings we know of who can ask these questions. The only ones counting stars. The only ones trying to understand where we fit. Let's talk about the Drake equation for a moment. In 1961, astronomer Frank Drake proposed a formula to estimate the number of active communicative extraterrestrial civilizations in the Milky Way. The equation takes into account the rate of star formation, the fraction of stars with planets, the number of planets that could support life, the fraction where life actually arises, the fraction where intelligent life evolves, the fraction that develops technology capable of communication, and the length of time such civilizations remain Multiply all those factors together, and you get an estimate. The problem is, we don't know most of those numbers. We can guess. We can make educated estimates. But the uncertainties are huge, depending on the values you plug in. The Drake equation predicts anywhere from 0 to millions of civilizations in the Milky Way. 0 to millions. That's not a useful range, but it's honest. It's a way of saying we don't know if we're alone, and we might never know. The Fermi paradox sharpens the question. If there are so many stars, so many planets, so many opportunities for life, then where is everyone? Why haven't we detected signals? Why haven't we been visited? Why does the universe seem so quiet? Enrico Fermi, the physicist who posed the question, didn't have an answer. Neither do we. Maybe life is rare. Maybe intelligence is rarer. Maybe civilizations don't last long. Maybe they're out there, but too far away, too different, too quiet for us to notice. Or maybe we're alone. Maybe we're the only ones asking. Both possibilities are terrifying. If we're alone, the responsibility is crushing. We're the only consciousness the universe has produced, at least in this corner of it. If we destroy ourselves, we take meaning with us. But if we're not alone, if there are others out there, why can't we find them? What does it mean that the galaxy is so vast, so full of stars, and yet so silent? Here's a common mistake people make when thinking about scale. They assume that because the universe is large, we must be insignificant. But size isn't the same as value. A grain of sand is small, but if it's the grain of sand that tips the balance, it matters. A single photon is tiny, but if it's the photon that triggers a chemical reaction in your eye, it changes what you see. Smallness doesn't erase importance. It just redefines it. The astronomer Harlow Shapley, the one who measured the Milky Way's size and realized we weren't at the center, once said this: the universe is not only queerer than we suppose, but queerer than we can suppose. He meant strange, weirder, more layered and complex than our minds can fully grasp. And part of that strangeness is the scale, the impossible, dizzying, beautiful scale. We're small, but we're also here, noticing, counting, wondering. Let's talk about the pale blue dot again, but from a different angle. That photograph didn't just show Earth as small, it showed Earth as fragile. A single pixel in the vastness, unprotected alone. No borders visible from that distance. No nations, no divisions, just a world. A shared world. The only one we have. And every person on it, all 8 billion of us, crammed onto that tiny dot, breathing the same thin layer of atmosphere, drinking from the same closed loop of water, living under the same sky filled with stars. We're only beginning to understand. The stars teach us humility, yes, but they also teach us connection. Because when you realize how rare Earth might be, how rare life might be, how rare consciousness almost certainly is, you start to see your fellow humans differently, not as strangers, as relatives, as the only other beings we know for certain exist, the only ones who share this strange experience of being alive, being aware, being temporary. And maybe that's the deeper lesson. The stars show us we're small, but they also show us we're together, alone on a pale blue dot, surrounded by 100 billion suns, most of which we'll never know we existed. And in that aloneness and that smallness, there's something worth protecting, something worth cherishing. Every astronomer who has spent years counting stars, every mission that is launched to map the galaxy, every late night spent staring through a telescope, they're all motivated by the same thing. Not the numbers, not the catalogs, but the awe. The recognition that we're embedded in something vast and ancient and ongoing, that we're part of the story, even if we're just a footnote, even if we're just a flicker. Being small doesn't mean being meaningless. It means being part of something larger. And maybe that's enough. Maybe it's more than enough. Because in a universe with hundreds of billions of stars and a galaxy so vast, we can't count its members with certainty we're here, asking questions, looking up, reaching out. And looking that stubborn insistence on understanding, that's what makes us more than dust. That's what makes us human. The stars don't care that we're counting them. They burn on indifferent eternal in their own slow way. But we care, we notice, we measure, we name. And in that act of attention, we create meaning. Not cosmic meaning, not universal significance, just human meaning. The kind that matters to us, the kind that makes the smallness bearable. So, yes, we're small, vanishingly small, but we're also awake. And maybe that's the rarest thing of all. Not size, not power, but awareness. The ability to look at the stars and know what they are. To count them even though we'll never finish. To reach for understanding even though we'll never arrive. That reaching is the point. That's what the stars teach us. And now, as we near the end of this journey, it's time to let go of the numbers, to stop counting, to drift into the quiet space where knowledge becomes feeling, where facts dissolve into wonder. The stars are still there, still burning, still waiting, and all we have to do is rest beneath them and let the stillness settle. We've come a long way through the dark tonight, from ancient eyes counting 1,000 stars to modern telescopes measuring billions. From Ptolemy's careful catalog to Gaia's precision maps. From the first shock of the telescope to the humbling truth of our pale blue dot. And through it all, one question kept pulling us forward. How many stars are there in the Milky Way? The answer, as you've probably realized by now, is that there is no single answer. 100 billion, 400 billion, somewhere in between. The number shifts depending on what you count, how you count, when you count. It changes as stars are born in the cold collapse of molecular clouds and as they die in the fire of supernovae. The Milky Way breathes, inhales gas, exhales light, and the count never settles. But maybe that's the real answer. Not a number, but a movement. Not a fact, but a process. The stars aren't a collection to be finished. They're a story that keeps unfolding, a symphony that plays on frequencies we're only beginning to hear. And we, small and brief as we are, get to be part of it. Not as the center, not as the purpose, just as witnesses, as listeners, as counters who know they'll never finish but count anyway. Think about what we've learned. We started with Ptolemy, who believed he'd cataloged the heavens with 1,022 stars. He wasn't lazy, he wasn't careless. He was limited by his tools, by his time, by the fundamental fact that he was embedded in the thing he was trying to measure. He saw what he could see and assumed that was all there was. It's a mistake we all make in different ways. We mistake the limits of our perception for the limits of reality. Then came the telescope, and the sky exploded. Galileo saw thousands. Herschel saw hundreds of thousands. Photographic plates captured millions. And with each leap in technology, the universe revealed another layer. The count multiplied again and again until the numbers stopped feeling like numbers and started feeling like poetry. 100 billion. The phrase rolls off the tongue, but it doesn't land in the mind. It's too big, too abstract. And maybe that's okay. Maybe some truths are meant to be felt, not understood. We talked about the Milky Way's structure, how it's a barred spiral galaxy 100,000 light-years across with 4 major arms and a supermassive black hole at its heart. How we live in a minor spur 26,000 light-years from the center orbiting once every 225 million years. We learned that the galaxy isn't uniform. The core is dense. The arms are rich with young stars. The halo is sparse, dotted with ancient globular clusters. And dust everywhere, dust hiding billions of stars from our view, reminding us that seeing and being are not the same thing. We explored the methods: statistical sampling, parallax measurements, spectroscopy. The Gaia mission, measuring over 1 billion stars with precision that would have seemed like magic to Ptolemy, like science fiction to Herschel. We learned about the initial mass function, the tool astronomers use to estimate how many faint stars hide behind every bright one. We learned that most stars are red dwarfs, dim and long-lived, invisible to the naked eye, but dominating the count. We learned that brown dwarfs blur the line between star and planet. and that stellar remnants, white dwarfs and neutron stars and black holes complicate the tally further. And we confronted the limits, the speed of light which turns every observation into a view of the past, the expansion of space which puts some stars forever beyond our reach, the cosmic horizon, that absolute boundary where the universe stops being observable and becomes theoretical. We learned that some stars have already died, but still shine their light, arriving like letters from the dead. And we learned that some stars will never be seen, not because they're too faint, but because the universe is too large, too old, too layered in time. Then we turned inward. We asked what it means to be small in a universe this vast. We looked at the pale blue dot, that single pixel of Earth suspended in a sunbeam, and we felt the weight of it, the fragility, the aloneness, but also the beauty. Because if we're small, we're also rare. If we're brief, we're also precious. And if the universe doesn't notice us well, we notice it. We count its stars. We map its structure. We reach across the void with radio waves and spacecraft saying, "We're here. We're listening. Are you?" The Drake equation gave us a framework for wondering if we're alone, but it couldn't give us an answer. The Fermi paradox sharpened the question, where is everyone? And the silence, the vast unbroken silence of the galaxy, reminds us that being small doesn't guarantee being common. We might be the only ones, or we might be one of many scattered so far apart that we'll never find each other. Both possibilities carry weight, but here's what the stars have taught me, and maybe they've taught you too. Being small isn't a tragedy, it's a perspective. It's a way of seeing that makes kindness easier, forgiveness, simpler, gratitude deeper. Because if we're this small, if our time here is this brief, then every moment matters more, not less. Every connection, every act of attention, every time we stop to look up and wonder, those moments become the only meaning there is. Not cosmic meaning, human meaning, the kind we make ourselves. We are made of stardust. That's not a metaphor. The atoms in your body were forged in the cores of dying stars billions of years ago. The carbon, the oxygen, the nitrogen, the iron, all of it cooked in stellar furnaces and scattered across space when those stars exploded. You're not separate from the universe. You're a piece of it that woke up and started asking questions. And that's extraordinary, not because it makes you central, but because it makes you connected. You're not outside the story, you're in it, made of the same stuff as the stars you're trying to count. Carl Sagan called us a way for the cosmos to know itself. The universe spent 13 billion years arranging matter into stars, planets, life, consciousness. And now, here you are, stardust shaped into eyes and neurons, looking back at the stars you came from and asking how many there are. The answer doesn't matter as much as the asking. The count doesn't matter as much as the attention. So, how many stars are there in the Milky Way enough? Enough to humble us. Enough to inspire us. Enough to remind us that the universe is larger and stranger and more beautiful than we can fully hold. We count them because counting is how we pay attention, how we honor complexity, how we say you're here and we see you even if we can't see all of you, and the count will keep changing. New stars will be born in the Orion Nebula, in the Eagle Nebula, in clouds we haven't named yet. Old stars will die, collapsing into white dwarfs, or exploding as supernovae, scattering their atoms to seed the next generation. The Milky Way will keep evolving, keep rotating, keep dancing its slow dance through space and time, and we'll keep watching, keep measuring, keep refining the estimate, not because we need a final answer, but because the reaching itself is the point. In a few billion years, the Milky Way will collide with Andromeda. The two galaxies will merge their stars, mingling their gas clouds, compressing their spiral arms, dissolving into a new shape. The night sky will blaze with the light of 1 trillion stars, closer than they've ever been. But by then, the sun will have swelled into a red giant. Earth will be gone. And there won't be anyone here to count the new total. The stars will go on without us. And maybe that's fitting. We're not the main character in this story. We're just passing through. But for now, we're here. And the stars are here. And the night sky, even with its city lights and its haze, still holds enough wonder to stop us in our tracks. You don't need to see 100 billion stars to feel the weight of them. You don't need to understand parallax or spectroscopy or the Hertzsprung-Russell diagram. You just need to look up, to notice, to let the vastness settle into your bones. Have you ever stood beneath a truly dark sky, a sky far from cities, far from lights, where the Milky Way arcs overhead like a river of milk, just like the ancients saw it? If you haven't, I hope you get the chance, because there's something that happens in that darkness, a shift, a quiet recognition. You see the stars and you realize they've been there all along, waiting, patient, burning through billions of years, indifferent to whether anyone notices. And you standing there, neck craned back, eyes wide. You're the first witness they've had in eons. Or maybe you're one of billions. Either way, you're there, noticing. And that's enough. The count is always incomplete. The methods are always improving. The estimate will keep shifting for as long as we keep looking. But the wonder that stays, the awe that deepens, and the simple, quiet truth that we are here counting stars will never finish counting, that endures. So, let the numbers go. Let them drift like smoke. What matters isn't how many stars there are. What matters is that you looked, that you asked, that you cared enough to wonder. The stars don't need us to count them. They were burning long before we arrived, and they'll burn long after we're gone. But we need to count them. We need to reach. We need to measure and map and marvel, because that's what makes us human. Not the answers we find, but the questions we ask. Tonight, when you step outside, if the sky is clear, look up. Find a star. Any star. It doesn't have to be bright. It doesn't have to be named. Just find one and hold it in your gaze for a moment. That star is a sun burning billions of miles away. Its light took years, maybe centuries, to reach your eye. By the time you see it, the star might already be different, older, dimmer, or gone entirely. But the light is here, and so are you. And for this one brief, fragile moment, you're connected, across the void, across time. Two pieces of the universe noticing each other. That's what counting stars really means. Not tallying numbers, but paying attention. Not finishing the list, but staying curious. Not solving the mystery, but living inside it, awake and aware and endlessly reaching. We have walked through history tonight, through Ptolemy's catalogs and Galileo's telescopes, through Herschel's marathon counts and Gaia's precision, through the structure of the Milky Way and the limits of light, through the humility of scale and the wonder of stardust. And what we've found isn't a number, it's a story that's still being written star by star, observation by observation, question by question. You don't need to remember the numbers. You don't need to memorize the methods. Just carry this. The universe is vast and you're small, and that's okay. That's more than okay. That's beautiful. Because in all that vastness and all those billions of stars, there's only one you. Only one moment where you're here now, listening to this, thinking about the stars, feeling the weight of the infinite, pressing gently against the fragile walls of your understanding. Sleep well tonight, knowing you're made of stars. Dream gently knowing the universe dreams through you. And when you wake, if you feel small, remember small doesn't mean invisible. Small doesn't mean insignificant. Small just means you're part of something larger. And that's the most beautiful position there is. Thank you for drifting through this quiet journey with me. Thank you for your curiosity, your patience, your willingness to sit with questions that don't have clean answers. The stars are still out there, still burning, still waiting. And there are so many more stories to tell, so many more questions to ask, so many more quiet nights ahead, where we can meet again beneath the uncounted sky and wonder together. Until then, rest. Let the stars do the shining. Let the galaxy do the turning. Let the universe do the dreaming. You've done enough just by being here, just by listening, just by looking up. Good night, friend. Sleep beneath uncounted stars, and may the quiet carry you gently into morning.